How about now? Can you hear me?
Yes.
Yeah.
Those who are online, can you hear me?
Yes.
Yes.
Yes, I can hear you from somewhere. I don't know where the voice is coming. We have this time the same problem like we had before. For some reason, the system, in any case, we'll try. If you can hear me well, that's all that I need. And I will make sure we're recording, and I will share my screen. So to be able to continue with the discussion, I had to go back and change some settings. All right, so here, and we are week 7, module impact 6. I will correct that. 2 things that I've done on the website. First of all, I went in each of the weeks and I specifically wrote down the sections of the book that we covered in this class. So for example, under week 7, you will see, say, textbook 6.5a, 6.5b, and examples 6.9, 6.10, and 6.12. All right, so these are things that you will have to cover, obviously, and they're not different from what I covered in class. But I suggest that you cover those things from the book. And if you go to like the previous week, I have done a similar thing. Say my notes, obviously, and then textbook 5, 6, and 5, 9. All right, so I did that for all chapters up to 6. So that is number 1. Number 2, as I said, I had students who said that they were confused about these various Zoom links. So I will, for office hours. So I will place the Zoom links for office hours here on your main page. And it's going to be a different Zoom link for Monday, a different for Wednesday, and a different for Sunday. And this is how it was done. It was not my design, all right? This is how Zoom brings them out. So they are here. You just have to click on those, and then you're going to get connected if you have the Zoom application on your device, whatever device you use. All right. So that is, and the hours there. So you don't, because sometimes I have students who join the last minute of the office hours. And if you have another class, let me know. Because sometimes on Monday, for example, there is nobody. A lot of times on Monday, I am by myself, and then Zoom turns off if there are 40 minutes without any other participant. So I will have then, to be able to join back, I will have to recreate the time. Okay, so what I suggest is that if you have in any of these times, you have a conflict with another class or a lab, and then you can only join towards the end, let me know, and I will wait. Okay, so I will be able to get off and then get on again before it closes. That is the other thing. And finally, I have, as I told you, I was going to submit a new survey for you. So you give me some information about how the class goes. So you will find it under quizzes, or for you, it might already be there. It says, your thoughts about the class and suggestions for improvements. You will get 55 points by doing that. There are 11 questions. The questions are not very difficult. Like it asks you about specific things, and if the answer is, well, I don't feel comfortable with something, you will see how it is. Then in the next question, it asks you for some suggestions. Because if, say, if I find that there is a problem with a lecture, with homework, with the lecture notes or something, and I don't get suggestions on how to make improvements, I will make some improvements, but that does not necessarily mean that those may address your needs. That's why your suggestions will be helpful. And I will let everybody else know how this comes out as a survey. All right. So today we're not going to have an exercise. We are going to only have a quiz like on Friday. Any questions about those? Okay. I don't hear any questions. I don't hear any comments. And I will look at the chat. I don't do this all the time. I cannot watch it all the time, but all right. So now what we are going to do for today. Today, I would like to remind you where we were last time, and then we are going to solve specifically a couple of problems in detail because your homework is going to ask you to do a similar thing, but on different geometry. So one thing I wanted to remind you that last time we talked about boundary conditions and specifically the dielectric interface, like here, that the tangential electric field is continuous and the normal electric flux density is continuous. All right, so these two. And then the electric conductor interface, and conductor, we said it means infinite conductivity, meaning like the carriers or the charges move instantaneously and they move to the surface of the conductor if there is an electric field, which means that there are no charges inside the conductor, there are no electric forces inside the conductor, there is no electric field, nothing. So inside the conductor, inside a perfect conductor, like we will consider here, the electric field is zero. Is zero everywhere. Inside the conductor and on the surface of the conductor, all of the tangential electric field components are zero. So we said last time that if you have an electric field and you bring a conductor in the electric field, then the electric field lines will change, so they terminate perpendicularly on the surface of the conductor. And the same thing, of course, applies for the electric flux density lines. And then we solve the parallel plate capacitor problem without any material in there. The solution is here. We talked about capacitance and why it is important to calculate capacitance, not only for a capacitor that may have only one dielectric in there, but also for lines which are in close proximity and may be separated by multiple dielectrics. And in this case, the capacitance of two lines in proximity, like these two, for example, the capacitance for a line like this, two lines that cut perpendicularly, is going to be in the form of the crosstalk is going to be in the form of a capacitance for static electric fields, all right? And when we go later to transmission lines, and every line is represented symbolically by two wires. And if you have two lines like the ones I showed here, two strips that share the same ground, but one strip is on one layer, the other strip is on another layer, and usually you have them in microelectronic circuits, and you have them on printed circuit boards, then your crosstalk is going to come in the form of a capacitance like you see here. So it is important to know why calculating a capacitance is critical, or having the means to calculate a capacitance. Here, and we talked about this last time, this is exactly the same derivation as with a capacitor without material. The only difference here, instead of free space, like where epsilon, like the dielectric constant, is the dielectric permittivity rather, instead of epsilon naught, you have epsilon, and epsilon equals the relative dielectric constant times epsilon naught, okay? So then last time, and now that's where I want to come and do it in detail because we did it a little fast. And I don't know whether well, that we need to go, I suggest that we go in more detail through this just so that it helps you for your homework, which is on a coaxial, all right? So homework is like different geometry, but the same approach. So one thing that I wanted to say from the beginning. You've always seen that when we calculate a capacitance, we assume that there is a charge distribution. All right, you have two parallel plate conductors like here. So you have two parallel plate. One is here and the other is below. And we assume that there is a charge. And then, in fact, exactly the same way that we did it for the here, we assume that there is a charge, positive charge in one plate, negative charge on the other plate. And then we assume that because of this positive charge, we have the electric flux lines and the electric field lines. So we always assume that we have an excitation to calculate capacitance. But what happens here, after we do all of this, as we will do it for more complex structures next, you will see the capacitance has no charge in there, which means what? That the capacitance is a quantity or that only depends in geometry. So when I go to the lab and say, okay, get this capacitor and put it on this printed circuit board to do an experiment, the capacitor is like a device, all right, that has two pins. It does not mean that there is anything connected to it. There are no charges on this capacitor, but it has a capacitance. So the capacitance is not dependent on the excitation. It is an attribute of the geometry of the structure. And when you apply a voltage, then of course, in this structure, it does perform like an ideal capacitor in some ways until you start having losses, all right? So capacitance, when we calculate, yes, we assume a voltage, but the capacitance is independent of that. So when I gave you the coaxial line in your homework and say, find the capacitance per unit length, meaning that you are going to consider a length of that, I did not give you a voltage, all right? But you, to solve it, like we will do next, you assume that is excited because that's where we start, because you need to have the electric field to be able to calculate the capacitance, but then you find out that it's independent of the field, all right? So you keep that in mind. So having said all of this now, I would like to take this problem A with the layered dielectrics. And I believe we had that already discussed last time, but we would like to solve it now. So it's not any different from what you've seen from before. But again, now what do? I take a voltage and I apply it here, all right? So I assume that I have a voltage, a battery that connects with the positive pole of the battery connects with the upper plane, and then the battery is grounded, and then the other plane is grounded. So the upper plane gets a charge, Q, from the battery, and then that charge, Q, which is positive, we assume because it's connected to the positive end of the battery, is inducing an equal negative charge on the other plate, all right? So then what we have is an electric field that is excited. The difference here from the original parallel plate waveguide we have is that now we have two materials in there layered horizontally. All right, and each one of them has a different thickness and has a different dielectric permittivity. However, what remains the same? So the boundary conditions. What are the boundary conditions? We found from before, we mentioned rather, that all the fields inside a perfect conductor, there is no electric field. So obviously we said that all of the components of an electric field inside a conductor, which implies also the tangential component of the electric field on the surface of the conductor, are zero, which makes then the field outside of the conductors to come to the conductors in a perpendicular direction, All right, we said that. So that's why, because the two conductors are parallel like this, and because they have, you know, they are uniform field distribution everywhere. So the field lines go perpendicularly from the upper conductor to the lower conductor without any disturbance. Now, the dielectrics that are there do not change that direction. Why is that? Because on the surface of the dielectric, we know two things. That the normal D component is continuous, as it shows here, that mentions here, the normal D component, the normal, therefore, component of the electric flux density goes through the interface, the dielectric interface, without any changes. And the tangential component of the electric field also goes through without changes. But in this particular case, there is no tangential of the tangential component of the electric field. So what happens is the electric flux density goes through the interface without any change, which means that the value of the electric flux density is the same in the upper medium and in the lower medium. All right? There is no other way around it. And you know how you would prove that? If you were to prove it, if somebody said, no, prove that. It's usually, I don't know whether you remember how you prove things with logic when you assume that something is not true and then you prove that it cannot. Have you done this before at all for any proofs? Kind of, all right? It's like a philosophical way of proving something. In this particular case, I don't want to prove it, obviously. But if you ask me and say, prove to me that what you're saying is true, you know what I would do? I will say, okay, let's assume that what I said is not true, that the opposite is true. So they are different. And then I would prove you that this problem cannot sustain two D, N1 and D and 2, which are different. All right. So these are the kinds of things that we are using in mathematics, obviously. It's like we call logic. All right. This is a logic what we call logic in mathematics. It's an approach of proving something. But in any case, in our case, you will know that they are not changing to the dielectric interface. And because there is no change through the dielectric interface, it makes sense that the upper material and the lower material will have the same value of the normal component of the electric flux density, which is the only component we have here. Having said that, now we put this aside, very important, all right, observations. What is then next? Now we remember also, well, the other conditions. We know that V1, which is the potential, therefore, all right, of the upper conductor, because the upper conductor here is excited, it's connected to a grounded battery, or in fact, a grounded static source. That means that the potential, all right, of this upper conductor is V sub D, because the other side of the source is 0. So the potential of the upper conductor 1 is V sub D. The potential of the lower conductor, number 2, is 0. These are the other two things that we observe here. All right, so we write down all of our observations. You're not going to solve anything without putting those in place. And then we said, now, what do we know? Now we know that electric field, E, is the negative of the gradient of the potential. All right, we defined that. We defined that some time ago, 2 lectures ago. And also, what else we know? That there is only one normal component of D, normal perpendicular to the parallel plates. And because D and E are related through a scalar, all right, here, look how D and E are related. They are related through a scalar. So practically, I will put here a line, because these are vectors. So whatever direction D has, E has it. All right, if D is only perpendicular to the walls, to the conductors. E is perpendicular to the conductors. And what did I do here? Look, I put a coordinate system. All right. So the direction which is perpendicular to the walls is the z direction. So keep that in mind. All right. So now what we do? We take, and then the electric field, I will just use that here to explain. We take the electric field and we, since E is minus gradient of V, I will perform an integration. I will integrate E from on a line that is along the Z direction and goes from conductor 1 to conductor 2. So practically, I will take E, which is perpendicular to the conductor. So E is along the Z direction, and I will integrate E from this point down here, from this point there. So I will from one point here down there. All right. That's the kind of integration I'm going to do. So in fact, if I were to write it here next to it so you can see it, these are the two parallel plates. This is number 1. And this is number 2. All right. And let me take this off here so I can write something. And then I'm going from number 1 to number 2. I'm integrating this from on this line, the red one, from this point, say A, to this point B. I'm integrating like that. So I'm integrating along the negative Z direction. You remember, because I decided to put Z to be like that. That's the Z direction that I have in my coordinate system, which is fine. You know, I mean, I can really integrate any direction I want. Now, we know that E has only the Z component, and therefore from this relationship, we know that E is related to the negative partial derivative of V with respect to Z. All right, so practically we have this formula. And that's what I integrate from 1 to 2. So I integrate this from 1 to 2. And then you can see here. And because of that, I go from there to this. Is there anyone who cannot see that? Who wants a little more explanation? I would like to put here a red color. All right. This one. That shows, because why do we do this like that? Because this practically is minus 1, 2 dV. Okay. And this is nothing else but minus V2 minus V1. V2 is the lower conductor at 0. V1 is the upper conductor at VD. So practically, you have this relationship here, and that results in this one. So the integral from one conductor to the second conductor, it gives you the voltage B sub D. So if I integrate from A to B, all right, along this line, I get voltage B sub D. All right, now, what am I going to do with A sub Z field? E sub z is a function of d. All right, so and I will write them here because when I write, I think you can see it better. You can follow my writing. So practically, let me even erase that and I write it and then you see what I'm doing. So we had here A and B, and then we have a material in between, a material that is split into two different types of a material. All right, one is up here, say, this is material one, and material two is the one down here. And each of these materials has its own thickness. So this one has a thickness of H1 and a dielectric permittivity of epsilon1, and the other one has a thickness of H2 and a dielectric permittivity of epsilon2. But we also said that D sub n1 and D sub n2, so we also said before that D sub n1, which is normal to the conductors, equals E medium 1 equals to D sub n2, all right, because of the conditions, because it's continuous through the interface, because the charge is uniform everywhere, because there is no reason for this to change anywhere. If you have two parallel plates so close to each other, all right, and then with uniform distribution of the charge, this is the only way for the electric flux density to develop because of the boundary conditions. All right, so now that we have this in place, I'm going to try to put the things that I said into practice. And I will say, okay, how much is E sub z in the yellow medium, which is here? So E sub z, and I will use that to see it. So E sub z in medium 1 is nothing else but D sub n in medium 1 divided by epsilon 1. And E sub z in medium 2 is D sub n in medium 2 divided by epsilon 2. And also we know, and in fact medium 2 is like green rather, so I will do it in green here. Z2 equals dn2 over epsilon 2. And then what else do we have? We also have from the conditions the dn1 equals dn2 through the interface between the two dielectrics, and therefore, and then I will call that d sub n. So then what I have from here, if I consider that they are constant through the material and they are equal, so equation 1 here gives me what? It gives me from, let me see here, let me call this point P. From A to P, E sub z1 dz plus from P to B, E sub z2 dz equals V sub d. And the first one gives me from A to P, dn over epsilon 1 dz plus from P to B, dn over epsilon 2 dz equals V sub d, which in fact gives me what here? It gives me that d sub n epsilon 1. How much is A to P dz? This is H1 plus d sub n over epsilon 2. How much is from P to B dz? This is H2 equals Vd. And therefore, from here we have the dn H1 over epsilon 1 plus H2 over epsilon 2 equals V sub D. So from one equation, I came down to 2. All right. So far, so good. I still have, I have more space available. I still have D sub n. So now I have to find out exactly how much this D sub n is and see what I'm gonna do here. I'm gonna take a piece of the upper conductor around this point A. This point A can be anywhere. I just selected it somewhere at the center. I will take, this is one point A, all right? And I will, this is the one that I have. Let me take it here and move it higher. All right. And at this point A, it's 1 point on the conductor. How much is the charge at this point A? I said that the charge is uniformly distributed. So how much will be there at that point A is going to be Q sub S, where Q sub S is nothing else but Q divided by the area. If the total charge is Q, and if it's uniformly distributed over an area, then practically I can define a surface charge density, which is Q divided by the area. Do you agree? Okay. So at that point, if I got 1 point on the area, what I will see is that charge, Q sub S. So let's assume that I go now there. I can find this charge by itself. I go there and I create around it an infinitesimally small volume, D sub V. And you see how I create it? It's a cubic shape. Part of the cube is inside the conductor. Part of the cube is outside of the conductor. So if I make this cube much bigger, all right, and this cube centers around this charge Q sub S. So practically part of the cube is going to be out inside the metal, and a part of the cube will be outside. And what separates these two parts is just the interface. All right, so I'm right, in fact, to a different one. I'm right here at the surface. All right, the surface. Now, how does I did this? This is dV. So this is dV. How many surfaces does dV have? dV is a cube, one cube, even if it shows the material, the conductor, half of it is inside the conductor, half of it is outside of the conductor. But as a cube, it has how many faces? 6 faces. The upper one, which is here, that face, let me see. One face is this one, the upper face. And what is the direction of the upper face? Like this. You remember every surface has a direction which is perpendicular. The lower face of this conductor is like here, inside. What is this? Let me call that this. That's the lower face of the conductor. Of the cube, excuse me, is outside of the conductor. And then you have the 4 faces around it. But how does the D field go? The D field goes like this, you remember? I will, since it's so tiny, I will put only one line that starts at this Q sub S. So practically, the D is only going through the green surface because in the purple surface, there is nothing there. It's inside the conductor. In the green, the field D sub n goes through the green surface that has this direction. And then all of the other surfaces have this direction, which is perpendicular to D. I will call them N prime directions. Okay, so keep that in mind, because now I'm gonna go here into and then take Gauss's law, and I'm going to integrate Gauss's law around this infinitesimally small volume. And I will get this relationship. And from there, let's see what happens. I changed using divergence theorem, the volume integral into a closed surface integral, which is over the 6 surfaces, all right? And the volume charge is going to give me, is constant. There is one charge at the center of this infinitesimally small volume. So it's going to be Q sub S times dV, all right? But because Q sub S is only on one surface, and it does not necessarily exist anywhere else, it's going to be Q sub S times ds only, all right? Because there is no charge anywhere else. So practically, that's going to give me this. Then this closed surface integral, if you remember, it's d dot inner product. It's an inner product between the two vectors. And every surface has a direction which is perpendicular to the surface. So the only surface where there is a D and it's parallel to the direction of the surface is through the green surface. There is no place else. The side surfaces, they are perpendicular to D. So the inner product between D and those surfaces is 0. The inside surface, the purple one, has no D, all right, because there is no field in there. So the only D that exists is through the green surface. And then it's, of course, it's a tiny surface, so obviously has one value. And this value is D sub n on the surface times ds. So practically, this one becomes D sub n ds. Okay? So look what happens here. That for this particular case, where I have a parallel plate capacitor with a uniform, remember that this is only true if the distribution on the surface is uniform. Then the value of D sub n, which is the perpendicular value of D on that conductor, is equal to the surface charge density. And what are the units for that? Coulombs per meter square. Okay, that's what we got. So now, what do? This is equation 2. I go take this equation 2 and go, this is 3 then. I will call this 3 because I have already number 2. So I call this equation 3. So I take 3 and I plug it into 2, equation 2 here. And what I get from this is this formula. And in fact, I would say is 1, 2, and like 2 and 3. And then gives me that, all right, which is kind of interesting. Why? Because what you find from here is that V sub D is the sum of 2 terms, Q H1 E1 times A plus Q H2 epsilon 2 times A. Okay, times meaning it's a scalar, so I will remove that dot so we don't get confused. How now we have defined a capacitance? We have defined the capacitance of every structure, like for this capacitor parallel plate with 2 materials. C is going to be still Q, which is the charge on the conductor, one conductor, divided by the total voltage V sub D. All right, that's going to be the charge for the, capacitance for this capacitor. Okay, so if I do this, then I find that C for this one is going to be, Q disappears, therefore, and is going to be 1 over A, excuse me, have to, H1 over A epsilon 1 plus H2 over A, A epsilon 2. Okay, and then if I continue, what do I get? I get that C equals, in fact, I will show it to you something in a different way. I will invert, and I will find that 1 over C equals H1 A epsilon 1 plus H2 A epsilon 2. But that reminds me of something. If I had here a capacitor that had only a thickness of H1, and it was filled by only one material, epsilon 1, and if I had another capacitor here, with only one thickness, H2 and epsilon 2, then I will have a series connection of two capacitors. What happens if I have a series connection of two capacitors? Yes, so it gives you, and as a matter of fact, it's going to be interesting that C1 here, excuse me, C1 here, oops, C1 here will be equal to A epsilon 1 over H1, and C2 here will be A of epsilon 2 over H2. Therefore, if this is exactly what it would have been if I had a smaller capacitor like this, but the same area, but just only the thickness of the upper dielectric and only filled by that dielectric. And then I had another capacitor, same area as the previous one, but only the thickness of the lower dielectric filled by the lower dielectric, and then put them in series, then practically I would have that the total capacitance of the original capacitor is 1 over C1 plus 1 over C2. It's like a series combination of a capacitance. You remember that? So that's what you have. So practically, you don't even have to remember how to do these integrations anymore, because what we find is that if you have a parallel plate capacitor that is filled with two dielectrics separated horizontally, but they have to be, of course, you know, I mean, they cannot be like, they have to have a very uniform interface, and the interface has to be parallel to the conducting plates, all right? Then in that case, if this was one dielectric, and if this in the other was another one, like we have here, then the total capacitance of this is like you have two capacitors in series. So it's like you have one capacitor, the green one, and one the yellow, and then you have them in series. So that will be the first one, that will be the second one, as if you had a conductor in the middle. See? Now, what you do, if you go there, what do you find? You can do exactly the same process. You can follow exactly the same process, but now the difference is that in the two fields, in the two materials, which are now separated vertically, the tangential component of the electric field is continuous. All right, there is only one tangential component, because there is still, the electric field has not changed. It still goes from the upper conductor to the lower conductor perpendicularly. And then what you find that this is now equivalent to two parallel capacitors. Is like something like this that you see here would be equivalent to one capacitor here, the same thickness like H, but with only whatever area corresponds to the red material, which is this one. All right, and then this is one, as if this was in parallel with another capacitor that has this area of the green material, same thickness as before, H, and then here filled by the green, and they were in series. And what will be the combination of these two? If you have two capacitors in, excuse me, in parallel, I meant to say. If you have two capacitors in parallel, and this is C1 and C2, C1 here, C2, then the total C would be C1 plus C2. And that's what you find. So when the material is divided horizontally, the capacitors are in series. When the material is divided vertically, the capacitors are in parallel. What happens when there is more of a complex division?
Gotta find equivalent capacitor one then do it for
Yes.
for
So you find the area, first you start with the horizontal direction, or maybe you start with the vertical. You say this part in the vertical is as if I have two capacitors in series, and then with on the A2 area is as if I have two capacitors in series, and on the A1 area I have one capacitor. So practically, here I will show you. Okay, let me do it here. If I have one capacitor like this, here and another here, okay? So it's exactly what you said, but I will then, and you have this material here, okay? You have this material here, and then you have this material on the other side. Then practically is the following, as if I have one capacitance here in series with this capacitance here, and that in parallel with this capacitor here, you see? And that will give me the capacitance here, which in fact is gonna be, you find it. So you see one, well, this is C1, C2, C3. So first of all, you will have to put the C2 and C3 in series and then do parallel combination with the other one. All right, so practically you have C1 in parallel with C2 plus C, well, in series, I mean. All right, so this is not a plus, it's just symbolic. All right, so parallel with a series combination of C2 and C3, which means if I were to do this, this is symbolic representation. Make sure you don't think that we sum. Symbolic representation, which means that this one is going to be C2, C3 divided by C2 plus C3, all right? Which is the series combination of the capacitors, plus C1, which is the plus comes to the parallel combination. Okay, so then you can have more. I mean, you can have like the other one that I showed here. So tell me, I will draw then this one, and I would like somebody to tell me how we're gonna do this one. Where I have here 4 materials. I have one material here. I have another material here. And then I have, look at this, one material here. And then I will have another material here. How are you going to do this one? Yes. Yes. Yes, exactly. Right. So that's the equivalent representation of the capacitors. Now, when is this not true? Let me show you another capacitor. Assume that I have this one. And then I have parallel plate. But I have two materials, and one is like this. And the other is like this. What we did here is not what we did before. It does not apply to this one. So you can only apply the previous equivalent circuit representations if the dielectric interfaces are either parallel to the conductors or perpendicular to the conductors. In this one, in this case where the interface is like that, what we've done before is not working. All right, but here it's working. Here you have C1, C2, C1 plus C2 plus C3, C4, C3 plus C4. But here nothing. Any questions? Now, keep it in mind because the same thing applies when we go to coaxial. What happens to coaxial? First of all, I asked you to find the capacitance. It's a cylindrical structure. So it's not a parallel plate waveguide, but you expect the electric field to go like that, all right? In fact, your book solves this problem. So if you go to your book, so it's good to visit the book once in a while, all right? Don't buy the book. Please don't buy the book and then you turn them unused. So if you go to this one, let me tell you where you're gonna find it. So we are in chapter 6. Okay, practice exercises. 6-9. Look at this. 6-9 has exactly the coaxial waveguide problem. 6-9. And not only that, but it also has 6-10, I believe. This says here 6 and 6-12 even are very similar to what I gave you, but I would like you to write them, not copy the book, write your solution the way I did it, like my way. But the solution is in the book too. And then I want you to go through these derivations. All right, so the book has it, the book solves it, you see the outcome, but I would like you to follow. My derivation is not very different, but it starts with Gauss's law. I would like to do that. I would like you to do that, okay? These are the most important problems, you know why? Because we have a lot of these capacitances in real life, in real circuits. We have them, and the coaxial. Let me see, coaxial cables here. We normally have a lot of coaxial cables. I don't know, but usually a lot of the thick cables that you see are coaxial. This one too. All of these internet type of cables, all coaxial. And people have designed them. And in fact, they're extremely robust because they have a number of layers. You see the picture that I gave you, the homework has also an outside, this black one. This black one is the outside to keep it robust so it does not damage the cable. But we use them on your TV sets. All right, we use them everywhere. These are called coaxial cables. Very useful. Now people have done weird stuff, right? With coaxial cables, they have more than one center conductors, they braid them around, they do interesting things, especially in Ethernet cables where you need to have a lot of other leads coming out. So they have, if you look at the Ethernet cables, if you go on Google, you will see that they have multiple conductors, center conductors, not only one, multiple, and they braid them. They have also an outside so they don't touch, the metals do not touch, but each one of them carries a different signal. And then for the internet, you see that, do you see how the Ethernet has multiple leads, multiple pins? So you need a conductor, center conductor for each one of these pins. And people have done some interesting stuff, but the bottom line is this. This is the simplest one that I gave you, is that one with one conductor only. We use them all the time, all right? And the capacitance is extremely important. You will see when we go to transmission lines, how transmission lines have a capacitance and inductance eventually, which we are gonna start next on Friday. But this is going to be the end of our electrostatics. We finish with capacitances, which is the most critical thing we get out of electrostatics. If you remember anything from electrostatics, please remember the parallel plate capacitor and the coaxial. These are the two most important concepts that you will see in front of you until the end of your career. Whatever you do as electrical engineers, you will see them. Any other comments or questions?
Yeah, I have a quick question just to kind of go back to the. So if you increase the dielectric, that doesn't affect Q, but it does affect V.
If you increase the dielectric, it does not affect Q, but affects V. So increasing, yeah, Q over V over Q over C over Q over V, yeah, it decreases it. So it increases the capacitance. Yeah. If you want more if you want more capacitance, but you have very, very specific distance between the parallel plates, you put a higher dielectric constant. Usually, if we design for capacitance, we don't use multiple dielectrics. We use one. We select one dielectric. The multiple dielectrics are good for crosstalk calculations. When you just have your lines everywhere and they cross over and you have multiple dielectrics underneath. And you want to find out how much is the crosstalk. And usually crosstalk in digital circuits is a capacitance. Not for something like that. You may design something with multiple dielectrics if you like do an Ethernet. But then you won't even, it's so complex because you do like a braiding with it. But don't design. Usually in microelectronic circuits, you will have only this kind of parallel plate capacitor. You design a capacitor with only one dielectric. But you will have crosstalk that you will express in the form of a capacitance. That's the only way in circuits because you don't, if you have a circuit, I wanted to ask you, how many transistors do you think we have here? Not trillions yet. We'll probably get that. Billions. At least a billion for some, the simple ones. How many interconnects we have for a billion transistors? Hundreds of billions. How do we design that? Not obviously every interconnect by itself. It's like you build a building out of bricks. All right, have you seen on the East Coast and the Midwest, these brick buildings that people have built in the early 20th century? Well, they have hundreds of thousands of bricks. Nobody designs every brick separately. That's how we do circuits. You design a block, a brick, and then you repeat the design of that. You use it multiple times. And then you design bigger blocks. Like even sometimes people will design a whole wall out of bricks and bring them, the walls, and sit them, like stand them, make them sit somewhere. All right, so these are bigger blocks. And then we work like this to go to a billion. There is no way, there will not be any way of designing them like that if we had to do it one by one. But when we design the initial brick may have like 10 transistors and 20, 100, or maybe 50 interconnects. Now, you're not going to go and do an electric, you're not going to go and do Gauss's law in this. No one will go into any circuit that has 100 interconnects going into all different directions and do Gauss's law to find your crosstalk. So you're going to replace those with circuit equivalents, which makes it very simple. Like capacitors and inductors, that's it. And you're done. And so for any crosstalk you want to take into consideration, you have to introduce a capacitance. And that's how we calculate the capacitance. And then we forget about Gauss's law. And we have the capacitance that we calculated. And that's what we put inside the circuits. And we design very, very, very complex circuits by doing that. That's why it's so important, all right? You need to remember it. Any other questions? So today we have office hours and like problem solving session. And if you want to join, it will be good. We'll solve some problems. Okay. So we'll see you. It's already what time it is? Yeah. Okay. So we'll see you either today or on Friday. Thank you. Sure.